Imagine a civilization so advanced, it could build a power plant around its own star, capturing not just a tiny fraction of its energy, but every single joule it puts out. Now, this isn't just something out of a sci-fi novel, it's one of the biggest ideas in this search for alien life, and we're about to dive deep.
You know the classic image, right? It's epic. A solid metallic sphere wrapped around a star, turning it into a giant engine for a cosmic empire. It's the ultimate prize for any species that masters its solar system. But what if I told you that iconic image is completely and totally wrong?
Yeah, the whole idea of a rigid shell is basically a mechanical impossibility. The gravitational forces alone would be catastrophic. The material stresses would tear apart any substance we can even imagine. The actual scientific reality is, honestly, way cooler: a Dyson swarm. Think of it as a loose, independent cloud of millions of orbiting habitats and solar collectors all working together.
So how did we even get this idea in the first place? And more importantly, why is it considered an almost inevitable step for any advanced civilization out there? Well, that story takes us from the pages of a 1930s novel right to the fundamental laws of physics itself.
So get this, the concept didn't even come from a physicist. It actually started back in 1937 with a sci-fi author Olaf Stapledon, who imagined this gauze of light traps around distant stars. The physicist, Freeman Dyson, read that novel in 1945, and it wasn't until 1960 that he formalized the idea. But his goal wasn't to design a megastructure, it was to figure out how we might find one.
And this is the absolute key. You just can't hide from the second law of thermodynamics. Any civilization using that much power has to radiate away the waste heat. So while the swarm would block the star's visible light, the structure itself would glow incredibly brightly in the far infrared. Dyson realized this heat would create a detectable technosignature, a cosmic fingerprint, visible across the galaxy.
And here's the brilliant, ironic twist. Dyson himself later called his famous paper a little joke. He even said he regretted that the concept was named after him and not Olaf Stapledon, the original sci-fi visionary. It just goes to show you how a powerful idea can take on a life of its own.
But okay, why would any civilization even need this much energy? I mean, what do you do with it all? To answer that, we need a way to measure how advanced a civilization is, not by its culture, but by its raw power consumption. And this is that measuring stick, the Kardashev scale. A Type 1 civilization uses all the energy available on its home planet. A Type 3, well, a Type 3 controls the power of its entire galaxy. But the sweet spot for this whole discussion is Type 2, a civilization that captures the total energy output of its star. We're talking about 4 times 10 to the 26th watts. At that stage, a Dyson sphere isn't just a cool project. It's a thermodynamic necessity.
So, where are we? Where is humanity on this cosmic scale? Right now, we are sitting at about 0.73. We haven't even fully mastered our own planet's energy. The journey to Type 2 is probably thousands of years away for us.
Which brings us to the ultimate engineering challenge. We know why a civilization would do this, but how, in the universe, would you actually build it?
Okay, first, you need an unbelievable amount of raw material. The calculations are pretty clear on this one. You'd have to literally dismantle an entire planet. And in our own solar system, the best candidate for the job is Mercury. Why? Because it's got a super high metal content, about 70%, and it's already nice and close to the sun.
Now, the proposed plan for how to build this thing is just genius. It's a bootstrap process. Step 1. You send self-replicating robots to mine Mercury. Step 2. You use automated mass drivers. Think of them as giant electromagnetic cannons to shoot the finished solar collectors into orbit. And step 3 is where the magic happens. Each new collector adds more power back to the operation on Mercury, which speeds up the mining and the building. It becomes this exponential feedback loop that could take apart the whole planet and build a swarm in just a few decades. Incredible.
So, let's say you've done it. You've captured a star. What do you do with 1 billion times more energy than the Earth receives? Well, the next step pushes this concept to its absolute mind-bending conclusion. You turn your solar system into a computer.
This is what's known as a Matrioshka brain. Instead of just one Dyson swarm, you build several of them, nested inside each other like those Russian dolls. The innermost layer runs the hottest computations and radiates waste heat. The next layer out captures that heat to power its computations, and so on and so on. It's a thermodynamic cascade, squeezing every last drop of useful energy from the star to power a computer so powerful it could simulate entire universes.
But is a star really the ultimate power source? Not even close. On the left, yeah, you've got star power. But on the right, a black hole. As matter spirals into a black hole, the friction in its accretion disk heats it up to millions of degrees, making it radiate with a brightness that can be hundreds of times greater than an entire star. Building something around one of those could be the fast track to becoming a Type 3 civilization.
Okay, so let's bring it all back to today. This isn't just a wild thought experiment. Scientists are actively hunting for these technosignatures right now. The search for Dyson spheres has turned into a real-life cosmic detective story.
A huge recent search called Project Hephaistos sifted through data from 5 million stars. And after all that analysis, they found a handful of really promising candidates. 7. Just 7 M-dwarf stars, all pretty close by, that showed the exact kind of weird infrared heat signature you'd expect from a Dyson sphere.
This was the big question, right? The thrilling part. Had we finally found evidence of a Type 2 civilization? The scientific community had to zoom in and take a much closer look. And this table here basically shows the forensic work they did. Using high-resolution radio telescopes, astronomers found that, yeah, the visible light came from the star, but the source of all that extra heat was just slightly off-center. And here's the kicker. They detected powerful radio waves coming from the heat source, but nothing from the star. The conclusion was undeniable. The heat wasn't from a sphere. It was from a background galaxy, one with a supermassive black hole at its center, that just happened to be in the same line of sight. A cosmic photobomb. So, if our best searches are coming up empty, what does that mean? This brings us to the heart of one of the deepest and, frankly, most unsettling questions in all of science.
It's called the Fermi paradox, or sometimes the Great Silence. If building a Dyson sphere is a totally logical endgame for a species like ours, their apparent absence is a chilling clue. Where is everybody? Why do we see no evidence of these incredible engineering projects anywhere? But maybe we're just looking for the wrong thing. Some scientists, like Avi Loeb, have suggested we shouldn't be looking for intact, functioning empires, but for their ruins. He famously proposed that Oumuamua, that bizarre interstellar object that zipped through our system with its weird shape and stringed acceleration, could have been a fragment, a piece of space junk from a long-dead civilization's broken megastructure. And that leaves us with a final question that just reframes this entire search. When we look out into that great silence, are we searching for neighbors, for living empires out there among the stars? Or are we really engaged in a kind of cosmic archaeology, searching for the ruins of those who came before?